Good afternoon. Looks like we have a long assignment today. A long one, by that I mean, what is it, almost 20 problems? Problems aren't all exceptionally difficult. I said are not all exceptionally difficult. This is a lighter section. I'm going to define something called functions. And once we make the definition of a function, the rest of the semester, that's all we're going to be talking about, are functions, functions, functions. Every other math class after this deals with functions. Trigonometry is the study of either 3 or 6 trigonometric functions. Okay? I'm saying 3 or 6 because it's really just 3 functions and their inverse, and their reciprocals, I mean. So what is a function? We're going to have several definitions. Here's the first way I'm defining it. So this is starting the new stuff. A function is a rule which assigns to each x value I could say one and only one, or I'm going to say exactly one. Exactly one y value. So we're talking about a rule that's assigning every x value. The phrase that you'll see if you look up the word definition of function on your phone or something is either exactly one y value or one and only one y value. I remember as a student, first time ever seeing this, I didn't understand why the teacher didn't just say one y value. But logically, just saying one assigns each x value one y value is different from saying exactly one. If you're standing in line at Whataburger with your friend and you order something that's $11, their card machines are down, so you can't use a card, and your lunch that you bought was $11, and all you have is a $10 bill. And you turn to your friend and say, do you have $1? Suppose they have $21. The answer to that question is yes, they have $1. They have $20 more dollars. But to say just to assign to each x value one y value, well, if it assigns 2 y values, it assigns them 1. That's why we got to say exactly one y value. Now, the set of x values has a special name. It's called the domain. The set of y values is called the range. So we have function, domain, and range. Let's do number 1. Okay, determine whether this correspondence, so they say correspondence, I said rule, is a function. Let me write that down. I'm going to draw this domain, range. Looking at this illustration, it looks like the x value 18 is being assigned the number 9 as its y value. The number 19 is being assigned the y value of 1. And the x value of 2 is being assigned the y value 9. Is each one of these x values being assigned exactly 1? Or 1 and only 1, not 2 or 3, just 1 y value. How many y values are being paired with 18? 18 is going just to 9, I think just 1. 18 is being assigned one y value, 19 is being assigned one y value, 2 is being assigned one y value. You might be thinking, well, wait, they reused the 9. That's irrelevant. How many y values are being assigned to each x value? The question was, it's a yes/no question?
Is it a function?
Is this thing a function?
Yes.
And the answer is yes. It is a function. The natural question, maybe the way that would make it clear, what would we need in order for it not to be a function? You might think, well, wait, they're reusing the 9. That's irrelevant. If any one of these numbers, x values, had 2 arrows going out, what I'm about to do is going to make it not be a function. If I drew this red line right there, then the number 2 is being assigned 2 different y values. So if this red line were here, then it'd be not a function. Okay? Any questions on that? Each x value is assigned one and only one y value. On problem 2, since the definition talks about x's and y's, that sort of lends itself to ordered pairs. So let me write these down. 13, 0, 16, -8, 41, 0, 13, 1, and 15, 1.
51, 1.
Oh my gosh, okay. 51, not 15.
You didn't define what a relation is, Tony, but a relation is any set of ordered pairs. A relation is just an arbitrary set of ordered pairs. Nothing special about them, just ordered pairs. So the question is this relation a function? Is every x assigned to one and only one y value?
Well, you're getting ahead of us. It says find the domain first. Okay, so the domain is a set of x values, and if we could read the instructions, you'd see it says do not repeat any numbers. So you're going to write out the set of x values. 13, the next x value is 16, then what? 41. Now look what's about to happen. We don't want to repeat them. The number 13's already been listed. And then 51. So there's the domain. You write the domains just by listing out the x values, but not repeating any x values.
The reason is the domain just tells you which numbers are being used. It doesn't tell you how often they're used. It's just these are the numbers that are used as x. It doesn't indicate the frequency of the numbers. Okay, the range.
Oh,
which numbers are used for y.
I'll write those down. I thought you were going to type in the answer for domain. Okay, so write the y values. Don't repeat any of them. So we have a 0, a -8, a 0, and a 1.
And
okay.
Let's answer the question.
Why don't you go ahead and type those in?
Okay, they've already put the set braces. So there's 13, 16, 41, and 51. The range, 0. We separated them by commas. -8 and 1.
You'll notice where the instructions say type each answer only once. That's why we're not repeating any.
Is this relation a function?
Let me
yes
look back
or no?
over here. I like this thing with the arrows. If you have a little illustration with the arrows, if there's only one arrow coming from each number in the domain, it's a function. But if there's one number that has two arrows coming out of it, then it would not be a function. So why don't we draw those arrows? 13 is being paired with 0. 16 is paired with -8. 41 is being paired with 0. 13 is being paired with 1. And then 51 is being paired with 1. Is this a function? Is each x value being assigned only one y value, or is there an x value here that has two different y values assigned to it?
There are two ordered pairs with the same x value and a different y value. So what are y'all concluding? Is it a function or not? Oh, I think he's already written it down.
Notice how two different arrows from this number 13. So that's like up here when I wrote this thing. So it's not a function. And that sort of leads to another definition of function. A function is a set of ordered pairs in which no x coordinates are repeated. Like right here, the number 13, that x value, has two different y values assigned to it. So a function is a set of ordered pairs in which no
X value. It's shorter than x.
x values are repeated. So if you have a list of ordered pairs, if there's a repeated x, then it's not a function. Now what about repeated y's? Well, that's irrelevant if there's repeated y's. The reason that this thing is not a function is because the x is 13. If we removed this, if I covered up that 13 comma 1, it would be a function, even though, notice, there's repeated y's. Okay? A repeated y is okay. There's no reason you can't have repeated y values. But a repeated x value means not a function. So we have two ways of defining function at this point. Just a rule assigning each x value exactly one y value, or you could write it out as ordered pairs. And if you have a list of ordered pairs, then there better not be any repeated x's. Okay? Well, we just finished graphing circles on Monday. So while circles are fresh in our mind, let's try to answer this question. Are circles functions? Are circles functions? Well, to answer that, I'm going to draw a circle. I'm going to put it right here at the origin, though it doesn't matter really where it's drawn. Oh, this looks more like an oval than a circle. Pretend it's a circle. There. Ah. One, 2, 3, 1, 2, 3, 1, 3. Putting a little grid line on it. We said if there's repeated x's, if there's two ordered pairs with the same x value, then it's not a function. Well, I'm going to look here at the y-axis. Look at these dots right here. If y'all were going to write those as ordered pairs, what's the x-coordinate of this ordered pair?
0.
0.
I agree.
And then it's a positive 3 here, and I was a little off. I wanted it to be a negative 3 down here, but it's sort of hard to tell. I mean, but it isn't. I missed it. I missed that little mark there. But that's almost irrelevant. The y-coordinate here is positive. The y-coordinate down here is a negative number. Do we have two ordered pairs with the same x-coordinate? Yeah. So what do we think? Are circles functions? No. Okay. If there's repeated x's, then it's not a function. And there's really nothing special about where the y-axis. Anywhere you can draw a vertical line, like right here, I'm at the number 1. If I drew a vertical line, here's a point that has the 1 as its x value, and here's another one. So two ordered pairs with the same x value. All we need is, one example of it, and we have it right here at 0. 0 comma positive and 0 comma negative. Same thing here. 1 is 1 positive and then a 1 negative. So what did y'all say for this? No, circles are not functions. Notice how I drew this vertical line in here, vertical line. When you draw a vertical line through a graph, if it intersects it twice, then you've just found 2 points that have the same x-coordinates. What I've said here is important enough that it has a name. The vertical line test. If you can draw a vertical line to intersect a graph more than once.
2 or more times.
Yeah.
More than once.
The graph is not a function. So if a vertical line intersects a graph 2 times or more than 2 times, then it's not a function. So we've answered the question, are circles functions? Well, let's do number 3.
Hey, we drew something that looked like this V-shaped figure. What were those things that had the V shape? We had a little graphing tool for them. Absolute value. This is the graph of an absolute value expression. Is it a function? Yes. It doesn't matter where you try to draw that vertical line. Are you going to hit it 2 times? No? So what do you think? Is it a function? Yes, it is a function. We were graphing absolute value functions there in that section when we were graphing the things. And Tony, did you want to draw a V shape and illustrate the vertical line test?
No, I mean, for any V-shaped figure, it doesn't matter if it's opening up or down. You can draw vertical lines and it's not going to intersect it more than once.
What about number 4?
Number 4, I think we've done already.
We have?
Okay, look at number 4.
This is an oval. Is an oval a function?
No.
No, right there. That y-axis is passing through it twice. So no.
A circle here on number that I
Wait.
drew looks, well,
Yeah,
maybe
it's sort of
ovalish.
It looks sort of
Yeah.
ovalish.
But a circle, oval, those are not functions.
There was this, we used to use an algebra textbook here at Delmar back in the 90s, and they had one homework assignment called Circles and Functions. And I was like, why? A circle is never a function. Why would you have those two topics grouped together? And we decided, well, neither of the assignments were real long, so they just merged them together. The author just took the two topics, put them together. And we eventually met the man, and yes, there were two short sections, and so he just put them together. Even though it seemed to me it was a weird choice because circles are never functions.
What about this? Is a slanted line a function? Let me see. I think number 5 is a slanted line.
I think there is one coming up. Let's see. Oh, wait. Uh-oh. You sure to get it? No. Oh, I didn't check it. That's interesting.
Okay. So
Here's a slanted line. Is a slanted line a function? Yes. No matter where you draw that vertical line, are you going to intersect the graph twice? It doesn't matter whether that vertical line is falling or rising. Vertical lines are always functions.
mhm. Now, the set of x values is what we call the domain. The set of y values is the range. I believe on this is number 5. Number 5 answered the question, is a slanted line a function? Just like number 4 answers the question, is an oval or a circle a function?
Yes. But here they also want you to state the domain and range. Tony, you better discuss that.
Domain, that's the set of x values. The range is the set of y values. If I took this slanted line and started continuing just drawing it out, if I imagine my x-axis and y-axis continuing on forever, way over here is negative infinity, way over here positive infinity. If I continue drawing this vertical line out, will it eventually get way over here on the left and way over here on the right? Will it keep going to the left forever and to the right forever? Is that what these arrows mean? I think you're going to have to, okay. I'm going to say that the domain here is negative infinity to infinity using that interval notation that we started using when we were doing the cut points. Oh, that looks bad. My comma looks like it's part of the infinity symbol. Okay. But go ahead and type that in, Tim, so they can see what it's supposed to look like.
Negative infinity, comma, infinity, right.
What we're saying there is that graph is continuing to go to the left forever and to the right forever. If we look at this graph, if we think of the y values, well, it's sure going to hit the bottom down there at negative 10. But will it keep on going and eventually have y values way up here if we continue drawing this out? Is it going to continue going and eventually be way up here at positive infinity and way down here at negative infinity? So the range, let's see if I can do it without messing it up. Negative infinity, comma, infinity. There, that looks nice. So for any slanted line, the domain is negative infinity to infinity. The range is negative infinity to infinity.
Is there a point on this slanted line that has an x value of 50 million? Is 50 million used as an x value on this slanted line? If it keeps going and going forever, here's 50 million. Yeah, there's a point down there with an x value of 50 million. What about a y value of 50 million? Will 50 million ever be used as a y value? Way up here. That's where Tony would have that little infinity drawn. Is there going to be a point on this graph where the y value is 50 million? What do you think? Yes, that's what this negative infinity to infinity is saying for the domain and range. Every number is used for x value, every number is used for the y value, and it doesn't matter whether the line is falling from left to right or rising from left to right. All slanted lines are functions with domains, all real numbers. Any questions on my logic?
Mm-hmm.
No? Okay. Okay. I don't think I've answered or typed in the answers to them. Okay, there. Oops. Range.
So what we're saying is that that graph is continuing to go to the left and right forever, and it's going to continue going up and down forever. Let's look at number 6. Ooh-wee. It's a U-shaped figure opening to the left. Is it a function?
Before you go on, realize this thing is, I'll have students say that it looks to them like it's changing directions and starting to go back down. No, this thing is slowly increasing forever. Down here, it's slowly going down more and more, okay? So let me switch over to the paper.
And Jade, I heard you say, when I asked, is this a function? What did you say?
No, it's not a function. When did you do all that, Tony?
Sitting there drawing it out.
Oh.
But to figure out the domain and range, see, on the domain, is it going to be moving to, let's look at the real picture of it, the graph, it looks better that way. It doesn't go left and right forever, does it? It goes to the right forever, but where does it stop going to the left?
Right there, that point.
See if
Wait
you
a
can
minute.
blow it up
I'm going
and
to
see
blow
what
it up.
happens.
Maybe I'll do this. I like this one better, okay? Blowing it up. So it's not going way over here to the left. What's the smallest x value on that blue graph? What's the smallest leftmost x value? It's not going to be negative infinity to positive infinity. -5, right. -5 is the smallest x value used. So instead of negative infinity to positive infinity, it's -5 to positive infinity.
No.
Any questions on our logic there?
You always put parentheses at infinity symbols, but what about this -5?
Look back at the picture.
Was there a graph there? Or a point, at -5?
I'd say, yeah,
Yes.
right there.
Let's see.
Mm-hmm.
I'm saying you include -5. The x value start at -5, or the graph starts here at -5, and then moves to the right forever. Now the up and down for range, that's the thing that can give students trouble, because it doesn't look what they mean for the
Especially here.
graph.
Well, I guess you can sort of tell.
Does it look like it's going up forever? Maybe here it looks better
Yeah,
on this
you're right.
one.
I think
It's
you're right on this.
Gonna keep going up and down.
And so it's going up forever.
My little graph.
Oh, it's going down forever.
Going down forever.
So
It's
what are
going
we going to
up
conclude about the
forever.
range? What's the smallest y value? Is there one?
It's gonna keep going down forever. It's going to keep going up forever?
The line kept going down forever, so the range started at negative infinity. It kept going up forever, so the right hand positive infinity. What do you think the range is going to be here? It keeps going down forever, and it keeps going up forever. Negative infinity to infinity. That's right.
Oh, we messed up my little comma once again.
I think it looks okay. I think you're being too hard on yourself, Tony.
Well, type it in so it looks nice. I remember once at a Pearson conference.
Oh, wait a minute. What did y'all say? Is it a function? No.
Oh, what? Not even ask for the domain. Yeah, it does. Okay.
So the domain, we use a left bracket, negative 5, comma, infinity, right parenthesis.
I suggested that they make a little hot button that was, you just click one button to get parentheses, negative infinity, comma, infinity, close parentheses. And they just sort of looked at me like I was insane.
You know, we should make that our little project to get that negative infinity to positive infinity hot button before we retire.
Why do you use a bracket?
Because there is a point at negative 5.
Right here,
Okay.
look at my mouse where I'm pointing. That point right there has an x value of negative 5. Did y'all hear that question? It's a good question, and it causes problems. And on tests, people will put parentheses negative 5 to infinity, and they count, and it's counted wrong because negative 5 is used. If it's used as an x value, then
Could you draw a little dot there at negative 5, comma, whatever it is?
right there, where my little arrow is, I could put a little dot right there.
And so you're saying you're including that as a
X value.
X value. Okay? There is a point there on that circle.
Any questions there?
So
we better
we've
talk about
seen
another definition.
we've seen functions listed as little diagrams. They can
Rules.
be ordered pairs. They can be done as graphs. Another way we can define function is to replace the word rule with one of our little equations.
I always say an algebraic equation.
A function is an algebraic equation which assigns to each x value exactly one y value. So we could have an equation as the rule. The domain is still the x value, the range is still the y values. But there's something called function notation. If you have an equation with x's and y's, you can solve for y, the y's by itself, and then replace the y with, it looks like it is f parentheses x. This f parentheses x is read function of x. Sometimes you just say the letter f of x. Okay? It does not mean times. I know you may have heard in one math class that of means times. This time it doesn't. And let's just look at number 7.
Function notation gives us a nice shorthand for asking the question. If I had a function and I wanted to know what's the y value when you plug in 0 for x, the shorthand way of writing that out rather than saying what does y equal when x equals 0 is just to say what is f of 0. Okay, that's saying take the 0, plug it into the original problem. Have you got it written down? Yes. Let me switch over to Tony's paper.
So look at this function. you read this as f of x, or function of x, equals 3x squared minus 3x. That's a rule that's going to give you the y values. The number in the parentheses is the x. What this is saying is plug 0 in for x. That'll give you the y value. So if I plug a 0 in for x, I guess that's going to be pretty easy, isn't it? So plug in a 0. We plug zeros in for x. What are we going to get? 0 squared is 0 times 3 is 0. 3 times 0. What are we getting for the y value here?
They
0?
said 0 a long time ago.
The number in the parentheses is the x. The answer that you get, that's the y value that's being assigned to it.
We just now created an ordered pair. We plugged in 0 for x. We got a y value of 0. There was a failed pedagogical attempt back in the 90s to make abstract concepts like these functions into things more concrete. And books started introducing these little things called function machines. You take the 0, you plug it into the little function machine, and then the little gears and levers would work, and it'd give you the new y value, 0. Let me type in the answer. Surely there's another part to this. Surely they're going to have more than just one part. Okay, now they want us to find f of negative 1.
In words, could y'all tell me what I'm going to do here? What do I do with this x? Excuse me. What do I do with this number in the parentheses? You plug it in for x. That's what I was wanting to hear. So,
whatever's inside the parentheses, that's what you plug in for the variable. And then you have to reduce it.
now be careful when you're plugging this stuff in. Do the exponent. Be sure to use that order of operations. Please excuse my dear Aunt Sally before you, do the exponents before multiplying. Negative 1 times negative 1 would be positive 1 times 3. That would be 3. Then we have a minus a negative 3. Would that be 3 plus 3? Y'all see how I'm getting a 6 as my answer here? With a function, every x value is assigned exactly one y value. Here's the x value. What was the y value that was assigned to it? What y value was assigned to negative 1? 6.
Mm-hmm.
So, and let's do another one. In words, what is this telling me to do? Plug what in for what?
Plug in 2 for x, f of 2.
So we go to our function, replace every x with a 2. Now be careful. You square and then multiply. Don't multiply first, okay? So 2 squared is 4 times 3. Is that going to be a 12? Minus what? 6? Oh wait, are we getting another 6? Yeah, remember it's okay for y's to be repeated. Okay? Just can't have repeated x's on a function. So here's the x, there's the y. We could make a little table like...
Wait, I'm typing it.
Okay. You see, at that very first problem, there's a little table like that. 0 is being assigned to 0. Negative 1 is being assigned to 6. Now 2 is also being assigned to 6. And how many, is that it or is there another
That's
one?
it.
Okay, so we're ready for number 8? Okay, number 8. Function of x, or f of x, equals x plus 15.
First thing we want is f of 0. If you've been following what we've been saying here, you can just tell me this answer. I don't even think you have to write anything down here. No, not 0.
What's the final answer?
What's the final answer? 15. Take the 0, plug it in for x. 0 plus 15 gives me the final answer of 15.
And I wrote it out there.
Plug it in 0 for x. We get a function value of 15. We've just created an ordered pair. When x is 0, y is 15.
What's the next number we're told to
I
plug
don't know.
in?
Let's see. F of negative 8. Don't y'all just love those problems with all these different parts?
Well, it's
At
not a
least
hard
these parts
part.
are short.
Okay.
What's that saying to do? F of negative 8.
Someone came
You
up to you
go
and
to your
said, what are we supposed to do
function F,
here? What are you
And you
going to...
replace any variable you see with negative 8. So we replace the x with negative 8.
What are we going to get?
What are we going to get?
So there's another ordered pair. See, here we have a little formula that we can use to generate ordered pairs. So negative 8, 7, but you just type in 7.
Yes. F of negative 16.
F of negative 16. So this is saying plug a negative 16 in for x. And what are we going to get? Is this going to be hard or not so hard? Negative 16 plus 15. Did I hear negative 1?
Yes.
Negative 1.
1. Okay. Is there another one? Yeah.
8. F of 10.
F of 10.
Oh, you screw. But
So tell me in
positive
words.
10 or negative 10? What
10.
was it? 10? Okay.
Positive 10. Tell me in words what that's saying to do. Plug the 10 in where the x is.
So if I plug a 10 in place of the x, I have 10 plus 15, 25.
Okay. So type in our 25.
Okay, now here's part 5.
Okay, part 5.
Ooh, F. Wait, so the moral of the story is whatever's in the parentheses, you plug it in for x. Is that right? So looking at this one, don't panic too much. Find f of d plus 20. At first glance, you're going to be, I have no idea what to do, but wait a minute. What do we say? Whatever's in the parentheses, you plug it in for x. It doesn't matter how strange it looks. So in place of that x, what am I going to put? D plus 20
And then you still have the
plus 15. Look at what I've written here. Are there any questions on what I just did? I've replaced this black x with the stuff that's in the parentheses. So in place of the x, I have d plus 20 plus 15. It's just this plus 15 right here. Well, we could add 20 and 15. So we have D plus what? Hold up. 35. There. D plus 35.
I remember Dr. Robertson used to say, F of cat. What would F of cat be? In place of that X, you'd have cat plus 15. And she always thought that was so clever. So whatever's in the parentheses, that's what you're going to replace the X with. And when we start working with difference quotients after spring break, I'll be reminding y'all of how does this function notation work. Whatever's in the parentheses, that's what you plug in for X. It doesn't matter how messy it is,
or how
strange it is. Whatever's in the parentheses, that's what you plug in for X. Okay, they have another function.
Okay, F is the letter that's usually used for functions, but there's nothing that says you've got to use F. Now here they're using the letter G. Given the function G, described by G of X equals 9X. Now what are we trying to find?
G of negative 14.
Let me just write it all down, and we'll do all three, then you can type in the answer.
G of
3.
And G of 31.
G of 31. Okay, so whatever's in the parentheses, you plug that in for X. So we have a 9 times X, 9 times negative 14, that would be it's going to be negative, positive times negative, 90 and 36. Is that negative 126? Doing that right? 9 times negative 14, negative 126.
I imagine most of them would punch that into their calculator. No, it's not a negative 9. 9 times negative 14. Okay.
Now I think the 3 we can do without a calculator. 9 times 3. That's 27. And then one more. G of 31. Whatever's in the parentheses, you plug in for X. So we have a 9 times 31. 270 plus 9, is that 279?
Yep.
Okay. Now go ahead and type in those numbers and get them right. Negative 126, 27, oops, and 279. Okay, we're just flying through here.
If you understand what we've been saying, then you can just type this answer in without writing anything down.
Okay. Who wants to call out the answer to this one? Wait, what did we say? Whatever's in the parentheses, what do you do with it? Plug it in for X. Having said that, can y'all just call out what we're going to type in on number 10?
Negative 5, but in place of the X, you have a P plus 6.
Mm-hmm.
That's right. Any questions there? This is saying go to the function F, replace any X you see with the letter P. So it's really just a change of variable. You change from an X to a P. Any questions there?
Okay.
Okay, this one we might need to do a little writing on.
Okay, number 11, it says f of x is negative 4x plus 5 Find and simplify f of 3p minus
B. 3B.
3b minus 4. 3b gotta look like 36.
Yeah.
Okay. Oops. Find f of 3b minus 4. If you were helping someone, how would you say in words what we're about to do here? How would you tell them what to do in words? You would say,
I'll get us started. Go to the function f and... Okay, so we're going to replace the x with 3b minus 4.
Correct. Notation means plug 3b minus 4 in place of x. So let me go ahead and do that. Now this time there'll be a little bit of work to simplify. So in place of the x, I'll put 3b minus 4. So we have negative 4. X is 3b minus 4. Don't forget the plus 5 there. Well, we got to distribute this negative 4. So what are we getting? A negative 12b.
What else? Distributing the negative 4 plus 16. And we still have a plus 5. Combine those constant terms. What are you going to get?
There's nothing to, that's a negative 12b, not a 126. Okay, nothing to combine with this b term, but we can combine these two constants, the 21 and 5. What am I going to, 16 and 5, what am I going to write? 21. Negative 12b plus 21.
For function notation, whatever's inside the parentheses, you go to the function and replace that variable with what you have in those parentheses. Negative 12b plus 21.
Before we look at 12, show my paper. Right. When we started this function notation, I said we have equations. We can have an equation as the rule. Okay, a function is an equation which assigns each x value exactly one y value. Instead of using x's and y's in the equation, if it's solved for y, then we can just replace y with f inverse.
F of x.
Excuse me.
Inverse. You're getting ahead.
Okay, with f of x, the number in the parentheses is x, and the answer is the y value. Okay, so when working with the x, with this function notation, the number in the parentheses is x, the answer is the y value. Why am I mentioning that? Well, look at number 12. It's going to look different. We're not given one of those little equations or formulas to plug into. Look what we have. We're just given a set of ordered pairs. What are those ordered pairs there?
9, negative 1.
9, negative 1.
Negative 4, 0. And 0, 2. We have 3 ways of expressing functions. We can express them as an equation. We can express them as an ordered pair. We can also express them graphically. You need to be able to use function notation in all three situations. Here it is in ordered pair. There's not an equation to plug in for.
What is it asking? In words, it's saying, show my writing here because I'm going to be pointing.
Okay.
Okay, the number in the parentheses is x. It's asking you, find the y. What's the y value when x is 0? I see two different ordered pairs that have y's.
No, that have zeros.
Excuse me, that have zeros. The brown ordered pair and the red one. Which one is this telling me to look at? The one that has 0 as an x. So which ordered pair am I looking at?
0, 2. Okay.
So x is 0. What am I about to write here for the answer? 2. Okay.
When x is 0, the y is 2. Suppose they'd asked us for f of negative 4. What would the y value be? When x is negative 4, the y value is 0. Okay.
There's really only 3 problems we can do with this one. F of 0, f of negative 4.
Could you tell me f of 5? Suppose I asked you for f of 5. When x is 5, what's the y coordinate? Could you tell me that? 5 isn't in the domain. What numbers are in the domain? What numbers are the x values that you can use here on number 12? 9, negative 4, and 0. If I wanted f of 5, undefined, this function doesn't give you an f of 5 because 5 isn't in the domain. There's no x value of 5.
Each x value is assigned exactly one y value. Like, what did you say, f of 5?
F of 5.
If you had it listed out here, 5 ain't listed in the domain.
Ain't?
Yeah, it isn't. 5's not listed in the domain. People don't say ain't anymore, do they? Okay.
Well, they do in East Texas.
Yeah, but I'm not in East Texas anymore. Okay, so did you type in the answer there?
No.
Find f of 0.
All this discussion and all the answer is we type a 2 and that's it. Next question.
Now.
Okay, so when you're using an equation, you have to plug in the x, the number they have for x. When they give you ordered pairs, the number in the parentheses is x. You find y by looking at the ordered pair that has that given x value. There's a third way of expressing functions graphically. There it is. What?
Maybe you should blow it up.
I will.
This is one where there's no writing on my part. The number in the parentheses is x. Well, how do you find the y?
You have to look at the graph. When x is negative 2, what's the value of the function? What's the y value? The y value is given by that function, f of x.
Do y'all see the ordered pair we're talking about for f of negative 2?
When x is negative 2, I'm pointing at it here on the graph. What's the y value? 0. Okay, good. What about f of 0? The x value is 0. Okay, the x value is 0. That's right there. What's the y value? 4. I agree with 4.
I remember this semester I once had a really bad class when doing this problem. I had a few vocal students that wanted to do it without the graph. How would we do it if we didn't have the graph? Well, you wouldn't have a problem. I mean,
But I have to either give you an equation or a set of ordered pairs or a graph. You can't find function notation when you don't have a function. What about f of 1?
Oh, wait. Can you blow it up any more?
I think so. Hold on.
Oh.
f of
Did
1.
that blow it up? I just meant click right there.
Oh, okay. Okay, when x is 1, can y'all tell me what the y value is there?
2.
2,
Two.
okay. Oh, goodness.
20 short years.
F of F of 4. I'm having a good time.
Oh,
I'm
yeah.
in no hurry.
I'm in no hurry. I don't want spring
The
break
students-
to start any earlier than it has to.
I'm waiting for
Spring
y'all to
break
tell me.
doesn't really
Four.
start. till
Okay,
Monday.
when x is 4, wait, when x is 4, the y value is 4. I agree. You need to be able to evaluate function notation, whether the function is an equation, that's what it usually will be, an equation, or a set of ordered pairs, or if they give you as a graph. If they give you a graph, you find the point with the x value, and the y value is the value of the function. Any questions there?
Hey, this is actually, if it were asked, look at the graph and state the domain and range. On this problem number 13, the domain would be -2, all the x values. They start at -2 and they go to what?
What's the biggest x value on this graph?
4.
4?
Would it be open, when you write -2 to 4 in interval notation, would it have brackets or parentheses?
Is -2 used as an x value? Is there a point on the graph that has an x value of 4?
So
Yeah.
those, you would put brackets there. Okay? But the range, the smallest y value is 0, the biggest is 4, and that would be
I used to be so good at writing, mouse writing. Are y'all good at mouse writing?
Nope.
Oh, I used to be so good at. Tony did too, but
I adopt
over the
signatures.
years,
I adopt signatures, e-docs.
Oh, yeah.
I was like, yeah.
oh, we used to be really good at
-2 to
that.
4. That's
That
what
would be
the
the-
domain of the range.
What would this be? The domain or range? Am I put a D or an R? -2 to 4. Looking at the x value, that's the domain, okay? So now the range. Okay? Do you agree it's not going to be negative infinity to positive infinity? The thing doesn't keep going up forever. It doesn't keep going down forever. So what's the smallest y value on this graph? The
0.
smallest y value is 0. Is 0 actually used? I claim it is. There are 2 points that have a y coordinate of 0, there and there. So 0. That's the smallest y coordinate.
What's the biggest y coordinate?
The biggest y coordinate on the graph. The tallest point. What's that y coordinate? 4?
Mm-hmm. Now, why are we mentioning this? Well,
I don't know. That's
it's
not
important to be able to find the domain. You can find the domain looking at the graph. Okay, what are the x values? You can find them just by looking at the ordered pairs like we did on problem number 2. We found the domain and range. Oh,
I got to turn that off, don't
oh, is it going to be showing? It is.
I? I think this is sort of bad, isn't it? I think I
Uh-oh.
messed up the
Video by doing the writing. It doesn't work the way it used to. I mean, try that.
Okay, wait. Undo.
Oh,
There. Okay.
Now look in here. So what we're about to start doing is how to find the domain. It's easy to find it when it's just written as ordered pairs. It's pretty easy to do it looking at the graph. At a graph.
Suppose it's an equation.
How do you find the domain?
Let me switch to your
The domain of a function that is written as an equation. when it's written in the form f of x equals. How do you find the domain of a function written as an equation f of x equals dot dot dot? Well, go ahead and show them number 14 and 15 just so they'll see what the heck we're about to start doing. It says find the domain of this function.
Don't write that. Don't
write it down yet.
We're
That's not the
ready.
first one I'm going to do. But this one, find the domain. So what I'm trying to tell you and what I'm going to try to write out now is how to find the domain when you have an equation. It's harder to do, okay? Or it's more involved. You're not just looking at ordered pairs. Well, in general, the domain is the set of all real numbers. We don't want any imaginary numbers that yield a real number for y. There are two things we don't want. We don't want, when dealing with fractions, we don't want what number in the bottom of a fraction. It's the one number we never want in the bottom, 0. When dealing with square roots, we're only interested in real numbers, no imaginary numbers. So if we don't want imaginary numbers, that means we want to avoid what type of numbers under the square root? Negative. We can't have negative numbers under the square root. Those are the things we got to avoid. In general, if the formula that you're given has no fractions and no square root, the domain is all real numbers. If the formula, or let's say if the equation has no fractions and no square roots, the domain is negative infinity to infinity. If you're given an equation and it's an equation that has no fractions and no square roots, then that's easy. The domain is all real numbers. Why? Well, you can plug anything in. You'll never get a 0 in the bottom of a fraction or a negative number under a square root if there's no fractions or square roots. To illustrate that, I'm going to do problem number 15. I'll go back to number 14 in a moment. Here's number 15. Find the domain of this function. F of x equals x squared minus 4x plus 15. When it asks you find the domain, what it's asking you is, tell me every number you can plug in for x.
And in turn get a real number back, not an imaginary number, not an undefined result.
Well,
You don't want a denominator of 0, you don't want the square root of a negative.
if there's no fractions and no square root, the domain is negative infinity, comma infinity. Are y'all going to tell me the answer to number 15? It shouldn't take a lot of work. By that I mean you don't have to write out anything. You just tell me what the domain is. Negative infinity to infinity. That's a way of writing all real numbers. You can plug any number you want in for x.
You'll get a y value back, and you can plot that point on an xy grid. The y value you get has to be something that can be plotted. That's why you can't have an undefined
Fine.
result. You can't have an imaginary number. You can't label an imaginary number on the y-axis. That's why it's called imaginary. No fractions, no square roots. Your domain is all real numbers.
So what we're doing here is looking at how to find the domain of these equations. And here's your first rule. You're getting several rules. The first one is if there's no square roots and no fractions, all real numbers. There's nothing special about x squared minus 4x plus 15.
Suppose it had said 7x squared minus 4x plus 150. What's the domain? Still negative infinity to positive
as
infinity.
As long as there's no fractions and no square roots. Well, okay, so we've got taken care of that.
This is a quadratic expression, but if we had something like an x cubed plus, in general we'd say it's just a polynomial function. All polynomials have the same domain. You're not going to get a denominator of 0. You're not going to get an imaginary number. So which one are we doing next, Tony?
Back to number 14.
Did you type in that? Oh, wait a minute.
Oh.
I have to choose the right answer. It looks like it's response B.
Oh.
Uh-oh.
What's happening? Have we been logged out yet?
Okay. Now we're back to 14.
Find the domain of this function. When you're finding the domain, you're finding every possible number you can plug in for x. You can imagine that's what it's asking you to do. Find every number you can plug in for x. If you're told to find the domain and you have a fraction, to find the domain, you're going to just do step 2 of the cut point method. Do you remember how did we find those denominator cut points, which I also mentioned on the little recipe for cut point method? They were also called the domain cut point.
X minus 5. Equal.
Can't
to-
equal
Yeah.
0.
There you go.
Okay.
I was like, there you go.
So if you have a fraction, you're just going to say the denominator can't be 0. Isolate the x, so x can't be 5.
That's saying all real numbers except 5. You can plug in any real number you want to for x except for 5. I like to write out domains in words. That's not popular anymore. The trend is interval notation, but I like it when you write it out in words. All real numbers except 5. That's what we have to express, but they want us to denote that using interval notation. Notice the instructions say, it's multiple choice. Yeah, it's all interval notation.
Which one of those A, B, C, or D means all numbers except 5? If you had to guess, which one would you say? If you had to guess. Not D. D is every number. Negative infinity to infinity.
Show them what it would look like on a number line.
That's what I'm going to do. Let's draw a number line and think about, I'm going to shade every number except 5.
Remember, with when using the cut point method with denominator cut points, how would we always label them? Open or closed? Which one? Open. We didn't want to shade it. But we want every number except for 5.
Every other number. Okay, I've lost my red pen.
Oh, I was playing with it.
Okay. If we're talking about every number except 5, I'm shading them red. Every number except 5. How would we write that in interval notation? Well, parentheses, always beside infinity, negative infinity, comma, 5, parentheses, because we're not including 5, union, parentheses, 5, infinity. What I've written here in red, that's how they want you to write the answer. But in words, you're talking about every number except 5.
This first interval is saying all the numbers to the left of 5. This one's saying all the numbers to the right of 5. The only number that's not included in these two intervals are 5 itself. So A, B, C, or D has to be B.
Like C would be all numbers except for 0.
zero.
Do y'all want to look at answer A, and in words, what would that be? I'll get you started. All real numbers except, and there's two numbers, except blank and blank.
Zero.
0
They're
and
excluding
5.
0 and they're excluding 5. Good. To be able to look at this interval notation and interpret what does that mean just in conversational English. I guess that all real numbers except 5, that's conversational English.
Let's go ahead and just do all the fractions. Let's do 16.
Okay.
Yeah, let's skip on to 16. Let's see, it says, find the domain of the function f of x equals, we have two denominators here. Okay, that just means we're going to have two denominator cut points, which we can now call domain cut points. So they're asking you, find every number you can plug in for x.
Look up here at number 14. Today I'm stuck on the number 50 million. Could I plug in 50 million for x? Is 50 million in the domain?
Yeah. The only number that's not in the domain on number 14 is 5. Number 16, there's going to be two numbers.
It reminds me of the way they had this answer. No, where was it? This one here?
No, that's the all real number.
Oh, that's all real number one. Here, remember y'all said part A was saying all real numbers except for 0 and what else? 5. So I bet the answer is going to look like that.
Okay.
Well,
looking at number 16, like this the second fraction. What's the one number I can't plug in for this x that I'm pointing at? 3.
Can't
I
plug
cannot
in 3.
plug a 3 in
X
there.
minus 3 can't equal 0.
So x can't be 3. But what about this fraction here? What's the one number I can't plug in for this x? -7? If this were back in the olden days, you'd be pretty much through. You just say all real numbers except -7 and 3.
Could I plug in 50 million here for number 16? Yeah, I can plug in 50 million. The only two numbers in the world that I cannot plug in for x are -7 and +3. How do we say that using interval notation? Draw another one of your number lines, Tony.
Okay, so I've drawn a number line. I've labeled -7 and 3. Those are going to have open circles because
You don't want to use them.
open circle means don't include. You're saying you cannot plug -7 and 3 in for x. You can plug everything else. How would I write all this shaded region in interval notation? Well,
When you said that,
parentheses.
you were going to say something else.
Oh,
As you started
oh.
Okay, so
Negative infinity to -7.
Close parentheses.
Parentheses,
Union.
Union.
Parentheses,
Mm-hmm. Union. All of this is just a fancy way of writing all real numbers except -7 and 3. I think I've mentioned how it's unfortunate that mathematics, algebra has decided to try to keep this little secret language. Back in the olden days, if you could write it out in words, you wrote it out in words, okay? Because, even if someone doesn't know algebra, my sister will have forgotten every bit of algebra she ever learned. But she could read all real numbers except -7 and 3, okay?
And she'd understand what that's
Okay,
saying.
but here, if I showed her this, what do you think someone that hasn't done any algebra since high school and she's older than me, how much of that do you think she remembers? None of it. She don't know what the heck any of this means.
So previously, when we were writing down the, what's the answer called again? Like the
Interval notation?
Yes. Typically, we wouldn't start, like the second set of parentheses, we wouldn't start it.
Oh, that's with the inequalities. You're thinking the intervals would usually alternate, but
Yes.
here there's not an inequality here.
Okay, so
Uh-huh.
because it does not alternate,
It's
and
not.
it makes
It's
it not.
everything except those. Okay, so it's not like you shade one and cross out the other and shade. For this,
Everything.
the only thing you're discarding are the individual numbers that give you a denominator of 0. Everything
-7.
else, like between -7 and +3, there's a 0. Yeah, you could use a 0 for x. You could use a 1 for x.
Because this is asking for what type of answer
Domain.
versus
This is when it asks for the domain.
And the other one that we've been learning is, well, the question
It'd be an
was
Inequality.
inequality.
And we're about to do
We're
that
gonna use
inequality stuff on
Okay.
let's see, did
the
you punch in
last
the
people.
answer there?
I think so.
Oh, wait.
No,
we're
I
not.
didn't.
Let's go ahead and do number 19. What do you think? And get it
Number
over
19? Oh,
with. We're
okay.
going to skip to number 19 to do it because, well, you'll see why we're going there. Okay. Find the domain of the following function. Number 19.
And I'm not sure why they stick on do not use a graphing calculator. I can't imagine why you would choose to use a graphing calculator to find the domain. So
X squared
I'll
minus
just mark out.
2x minus 8.
I better not. But
See, this one here, it's not multiple choice. You got to type it in. Did you see that? That's why I'm trying to draw the number line and show you how you get that. How does this one differ from the one we just did? Well, over here, we didn't have to factor these denominators. But on this one, we're going to have to factor it. The denominator can't be 0. So it's been a while since we factored. At least we haven't factored anything today. Help me out. X and X. 1 times 8 or 2 times 4. Once we get it factored, it'll be as easy as the one we just finished doing.
what are we going to use for 8? 1 times 8 or 2 times 4? It's a simple trinomial, so it's easy to choose the pair. 2 times 4. You want the pair that subtracts to give you that middle number there too. What about the signs? What do we know? Plus and a minus. Play it out in your head. Where should you have the plus? In front of the 2 or in front of the 4 in order to get back a minus 2x from the outer and inner?
The plus
The
in front
plus
of the
there
2.
and the minus there. I agree. So at this point, it's not that previous problem we did.
X plus 2 can't be 0, so X can't be -2. X minus 4 can't be 0. X can't be 4. So those are the only two numbers X can't equal. It can be anything else.
Could X equal 50 million? Could I plug in 50 million for X? Yes, the only numbers I could not plug in are -2 and +4.
So are we going to list every interval here, since we want all real numbers except negative 2 and 4. Negative 2, 4, open circle, and shade everything except negative 2 and 4. Okay? The only two numbers you can't plug in for x are negative 2 and 4. So what will this look like in interval notation? Parentheses, negative infinity, comma, negative 2,
union, comma, negative 2.
Uh-huh.
I mean, negative 2,
Yeah.
negative
2 to 4, uh-huh.
I mean to 4.
And 4 to infinity.
Notice, let's go back. Notice we're not testing any intervals here. We're not trying to figure out an inequality. All we do is we label those denominator cut points and we say if we don't want to use those, anything else. There's no testing intervals.
If you're told find the domain and you have a fraction, then you find where the denominator's 0, and then you're going to use every interval excluding those numbers. Okay? That's going to be different from
What we're about to do.
the last two problems we're going to do. Looking
Wait.
back over. Oh, wait.
I
You need
haven't
to
typed
type
in
it
the
in.
answer.
Oh, okay, type in the
wait,
answer.
I got to type in the answer. Give me a moment. Left parentheses, negative infinity, comma, negative 2, union,
2 to 4.
2, comma, 4, union, oh, negative, thank you, thanks, union, 4, comma, infinity. And it's unfortunate. I think it's hiding. This notation is hiding what we're trying to say. We're trying to say you can plug in any number you want to for x, except for negative 2 or positive 4. Those will give you denominators of 0.
Mm-hmm.
If there's no fractions, no square roots, all real numbers. If your function has a fraction, that's called a rational function. Just like a rational number is another word for fraction, a rational function is a function that has a fraction. And look at number 17. There's something different from this one. What does this function have that the previous functions did not have? A square root. Remember what he said. Tony said you want to avoid imaginary numbers. No square roots of negatives.
So, let me go ahead and
Oh, I
write.
thought you were going to show where you'd written that.
Oh, that's what I was going to do earlier, and I got distracted.
No, that's too far. There it is.
There it is. We're avoiding 0 in the bottom of a fraction and negative numbers under a square root. So what have we done here at the end? Since I started all of this, we've learned, okay, if the equation is no fraction and no square roots, you just say the domain is all real numbers. If the equation has fractions, then you say, okay, denominators can't be 0, and to get the interval notation, you go through every interval and separating them at the numbers that you're excluding. Okay? How do we find the domain
Of a square root function. Oh, wait, you're right.
to find the domain of a square root function? You're going to have to use the cut point method to solve we said we can't have negative numbers under the square root symbol. So you're going to take this radicand. That's the stuff that's under the radicals, under the square root. Take the stuff that's under the square root, set it greater than or equal to 0, and then use that cut point method. Okay?
I think you should write the two cases. Oh, you're going to do that, okay? Look at this one here. Look at this one.
There's two different types of problems you're going to see.
With square roots. The two things you're going to see are either the square root's going to be in not in the denominator, or it will be in the
Just show number
denominator.
18.
Look at number 18.
To compare the two.
Here the square root's in the denominator. And number 17, that square root is not in the denominator. And that's going to determine the inequality you set up. If it's not in the denominator, the square root is not in the denominator, then you set the thing under the square root greater than or equal to 0. Because it's okay just to have the square root of 0, that's 0. But suppose your radical, if there's no denominator, you take the thing under the square root, set it greater than or equal to 0. If your square root is in the denominator, then the stuff that's under the radical, you just set greater than 0. And why would that be the case? Look at this number, where is it, 18? I wouldn't want to plug in a 9 for x on number 18. 9 minus 9 is what? 0. The square root of 0 is 0. Is it okay to have 1 over 0?
No.
No. So if it's just if the square root's in the denominator, your inequality will just be greater than. If the square root is not in the denominator, then it'll be greater than or equal to 0.
If the square root is in the denominator, just use greater than. If there's no denominator at all, greater than or equal to. And it's going to be that cut point method. Let's do 17. What was it?
The square root of f of x equals the square root of 10 minus 2x.
So the instructions are saying find the domain. That means what numbers can we plug in for x? We don't want a negative number under here. You could guess, if you wanted, like 0. It's okay to plug a 0 in.
You know what I tell the students? You start off the same way you do with those rational ones we just finished. When there's a fraction, you set that stuff not equal to 0. Here you use the radicand, but instead of not equal to 10 minus 2x, you set it greater than or equal to 0.
And I think I do have a little sheet of the cut point method in my bag. Do I have any of those? I'd like to look at or point at it. Because on problem 17, you're going to use cut points to solve this pink inequality. On problem 18,
set up the inequality for number 18 also, so they can see the difference.
Number 18, is that the 1 over? What's number 18?
I don't remember. It's 1 over
X
square root
9.
of x minus 9.
Yeah.
I remember now.
Mm-hmm.
Yeah, okay. Okay, so write them both down.
Mm-hmm.
If the square root's not in the denominator, you set the stuff underneath the square root greater than or equal to 0.
See, greater than or equal, that's what I used on number 17. Just greater than is what I'm using on number 18.
Because you don't want that denominator to become 0. It can only be greater than 0.
Now, this is going to seem a little strange just because this is this problem right here. How do I know, oh, I got to use cut points? Well, it has the inequality, okay? Ooh, it's sort of hard to read. but this is that recipe for the cut point method. Okay. You start off, replace the inequality with equals, solve for x. So I'm now going through the cut point method for this. 10 minus 2x equals 0. I think I'll get as few negatives as possible by moving the 2x to the right.
And what is he about to get for the solution cut point? 5. I agree.
Oh, good. I'm so glad you answered that. I was already thinking y'all had already turned it all off. Okay. Now, just like with those other cut point problems, if there's an equal sign, use a closed circle. Okay, so we're going to label the number line, or draw the number line. There's only one cut point, 5, with a closed circle.
We have to test something. What do y'all think we'll test? 0. Which interval contains 0? Left or right? Left, okay.
So if I test 0, 2 times 0 is just 0. 10 minus 0 is just a 10. It's not equal to 0, but is it greater than 0? Yes. You see, this one, it's back to doing what you do with cut points. Cross out the next one.
If you tried to use 6, you'd get 10 minus 12. That's a negative 2. You don't want a negative 2 under that square root. The square root of negative 2 is imaginary. Any number to the right of 5 for this function would give us an imaginary y value. We only want the interval that gives us real numbers back. That means you can't have a negative number under the radical. If we plugged in negative 50 million, yeah, that would give us a positive number, and that's fine, okay? It's the numbers to the right of 5 that we'd have to discard. How do you say that using interval notation? Comma, bracket. Any questions on our logic there?
Okay, to make sure you're with the square roots, that's where you actually have to test the interval and cross out one of them. When there's just fractions, do you have to cross out intervals?
Yeah, well, you're not crossing out intervals. I guess you're crossing out, you're discarding numbers.
No, but you still got to write them as your answer.
Yes.
Okay, so is it clear the difference between this problem and this one over here? It's with the square roots. There's a reason why we're doing these last. They're the most involved.
But when we were solving inequalities, we were solving really messy ones. We never had one as nice as 17 or 18, so
Look, okay.
it's a pretty painless
Oh,
inequality.
did you put in the answer?
Oh, I got to type in the answer. That's right.
Or is it multiple choice?
No, it's not multiple choice. I have to type it in. Parenthesis, left parentheses, negative infinity, comma, what was it?
5,
bracket. And now number 18.
Oh, this one's multiple choice.
Nah, this one's a multiple choice.
So we just want to know on this one, where is x minus 9 greater than 0? It can't be negative, because then you'd have an imaginary number. And it can't be 0, because then you'd have 1 minus 0. Do y'all see the
1 over 0.
Excuse me, 1 over 0. Do y'all see what I mean by, if there's no denominator, use greater than or equal to. If the square root is in a denominator, then you're just going to use greater than 0. How will that affect things? Well, instead of a closed circle, like we had on 17, what are we going to have on 18? Open circle. Okay? So we say x minus 9 is, well, I guess we said not equal, so that's what we were doing. Oh, yes, we did. Oh, what am I doing? Equals, well,
I don't know.
I have no idea what I'm doing.
X
There.
minus-
So x minus 9 is 0. X is 9. Our solution cut point. Open or close circle. Open. Draw your number line. Am I running out of room?
You never know.
Okay. Open circle. Test an interval.
How about which interval contains 0, left or right? Left, let's test 0 then. That's easy to plug in.
If I plug 0 in, am I going to wind up with a negative number? I get negative 9 is greater than 0. No.
Cross out. So you want the right ones.
Every number to the right of 9 will give us back a y value that's a real number. We can't plug a 9 in because then we'd have an undefined 1 over 0. We can't plug numbers smaller than 9 in because then we'd get an imaginary number. Like if we plugged a 0 in, we'd get square root of negative 9. That's a 3i. No. The reason we spent time at the beginning discussing imaginary numbers is basically so we can spend the rest of the time saying,
oh, we don't want
imaginary numbers. Okay? So how do I write this interval in interval notation? I go...
Number. 9, comma.
9, comma.
Positive infinity, close parentheses.
Okay.
Y'all see, these two problems are sort of, they're similar, but they're different also. Y'all see the difference?
It's where the square root is located. If it's in the denominator, just greater than 0. The radicand has to be greater than 0. If the square root is not in the denominator, the radicand has to be greater than or equal to 0. And I have an answer number 18, have I? There. A, B, C, or D.
Oh,
look at that.
Oh, B and D.
Look at that. B and D. Which one do I want? And it's unfortunate in the homework. Okay, well, you miss it, choose the wrong one, you can correct it. Can you do that on the test? Mm-mm.
So like B means all numbers bigger than 9, including 9. D is not including 9.
All numbers bigger than 9, not including 9 itself. So,
wow, it'd be a neat thing to have a reading math class where the students get stuff like that and get to write out what the heck it means. And I think we've done them all. Are there any questions? It's the same, but I guess we ended on a hard note, but it's not
it wasn't that
hard. Yeah, I'll tell y'all when the stuff is gonna get hard. Y'all wait until the Monday after spring break, then it's gonna get hard.
It is? What are we doing?
I don't even know what we're doing on that day. I'm joking about that.
Okay, I'm going to stop recording.
If something's hard, I'll never
Tony,
say
is there
it.
anything you wanted to record?
No.